For lab number 8, we're going to be working with titrations. So first, I'll do a demonstration of a titration. Specifically, I'll do a titration of vinegar with NaOH. So you can see I've got my vinegar solution here and my NaOH solution. And the NaOH solution that we're using is a 0.1 molar NaOH solution. And then I've also got an indicator, specifically I have phenolphthalein, and that will change our starting vinegar solution from clear to pink once we've added enough NaOH to fully react our vinegar. So when the solution goes from acidic, which our vinegar solution is acidic, to basic once we've added enough NaOH solution. So for our setup, we have a burette, and the burette will put our NaOH solution in, so we know the concentration of our NaOH solution. Again, that was a 0.1 molar solution, and our burette's going to allow us to measure the volume of our NaOH solution that we use. And then the flask, we're going to put our vinegar solution in. And I will measure out a specific amount. I'm going to use that pipette and measure out 5 milliliters of that vinegar solution, put it in that flask, and then we will titrate it with our NaOH, releasing the NaOH from the burette into the flask until we see our color change. Now, before we get started with this, you should know that a vinegar solution is a solution of acetic acid. So I already said it's acidic, and that's because it is made up of acetic acid and water. And so that acetic acid, we don't know the concentration of it. So we don't know how much is in that solution. And that's what we're looking for in this titration. So we will know the volume of that vinegar that we start with, and we're going to use our titration data to calculate the concentration of acetic acid in that vinegar. To prepare for our titration, we need to put sodium hydroxide into our burette. But first, it's always good to make sure that there's no leftover residue in the burette. So I actually rinsed it out with distilled water before we started this, and so it's kind of wet inside of there. And so there's a little bit of water trapped in there, and I don't want that to dilute our sodium hydroxide solution because we're assuming that we have a 0.1 molar sodium hydroxide. And if I just add it to some water, it dilutes a little bit, and our accuracy is going to be off for our titration. So first I want to actually rinse this out with the sodium hydroxide solution. So I'm going to pour some in here, coat the sides a little bit with it, and then release that. And I'll do that process 3 times before we actually fill the burette with the sodium hydroxide we're going to use. But before I pour any in there, you should look and see this down here is our stopcock, and so that's what is going to open up the burette to let liquid flow through. So right now it's perpendicular, so it's closed, but if I turn it and make it parallel with the tube, then it's going to allow liquid to flow through. So I'm going to get a funnel, and put the funnel in there, and pour a small amount of sodium hydroxide into the burette. Okay, so now I've got some sodium hydroxide in there. And what I'll do is, like I said, kind of try to coat the insides with it, just to get any residual water off the walls of the burette. And so you just have to carefully tilt it till you get the liquid level kind of up to the 0 point, and rotate. Actually get it all around. Okay, so that should be good. Now I can release this liquid that's been somewhat diluted by the water that was already in there. I'll release that into just a waste beaker. And now I'll close that, and I'll repeat that process 2 more times, and then I'll fill the burette up to about almost the 0 mark, but not past, with our sodium hydroxide solution. That way we can start our titration. Okay, I filled the burette with our NaOH solution, which will be our titrant. I also, when I filled that, I did release some out the bottom so that the tip doesn't have any air bubbles. So our burette is ready. And now what we need to do is we need to get our analyte, or our vinegar in this case, ready to do the titration. So what I'm going to do is I'm going to take the Erlenmeyer flask, I'm going to put 5 milliliters of vinegar in there using this 5 milliliter pipette. So I have a 5 milliliter volumetric pipette. You see it's got this big 5 on there telling us the volume, and this line up here, if we fill up to there, that gives us 5 milliliters. So I already went through and did the rinsing procedure that I did with the burette with the vinegar. So right now the little bit that you see kind of in here, that's vinegar that was used to rinse that. And so I'm going to fill this up to the 5 ml mark and transfer it into the Erlenmeyer flask for our titration. So we have our 5 milliliters of acetic acid, or our vinegar solution. Okay, so that is the analyte that we will be titrating. And some of that got up on the edges, so usually we would wash the insides of that with some distilled water. That way that we don't miss neutralizing any of our analyte. And so I'll just rinse the insides. And it doesn't matter how much water gets added to this. It's not going to change the number of moles of acetic acid that's in our vinegar, which is what we're actually trying to figure out, the number of moles. That way we can figure out then the concentration of that 5 ml sample that we transferred. So this is my solution that I'm going to start with and do my titration. You've got the vinegar solution, the analyte, and the NaOH solution, the titrant. Now, one last important thing before we actually start the titration is that we need to put a few drops of our indicator in, so we have a phenolphthalein solution, and so we just put a few drops down into the flask. If we forget to do that, then the solution will just remain clear the whole time, and we will miss our end point of our titration, which is what we're looking for. We need to know the accurate end point so that we can figure out the concentration of our unknown solution. So I'll go ahead and put that underneath the burette, lower that down a bit to make sure I don't miss the flask. And then we need to take our initial reading. And so we'll have to take an initial burette reading. Now, before we start our titration, we need an initial reading from our burette for our NaOH. before we take our reading, you should take note that the scale on a burette is upside down from what you're used to. So the 0 is at the top and the 50 is actually all the way at the bottom. And so where we're at is we're somewhere between 0 and 1 for our milliliter reading, because also notice the unit is up there, milliliters. But we're not quite at 1. And there is a breakdown of 10 between your 0 and 1. And it looks like the bottom of our meniscus is actually somewhere between that 9th line and the 1. And so we're somewhere past 0.9. And actually we should estimate how far past that we think it is. And I would say it's just a hair past. So I'm going to say that our initial volume reading of NaOH is 0.91. And so we'll write that down as our initial NaOH reading, 0.91 milliliters. And so that value is where our volume reading is starting. And then we're going to let some solution out. And so our solution is going to go from being at 0.91 to somewhere below that. And then what we can do is we can subtract the two volumes, and it's going to tell us how much NaOH we actually use in our titration. Now we can start our titration. So we've got our clear solution, our vinegar solution down here. We've got our NaOH up in the burette. And we put some indicator into our flask, so it should change pink when we're at our end point, or it should change pink and hold that color for at least 30 seconds. You don't want to just put a lot. Eventually it will just turn pink and stay pink forever. So we're going to start by adding our NaOH quickly, because we're going to need quite a bit, but when it starts turning pink and wanting to stay, we'll start slowing down and adding it closer to drop-wise. So what you should be able to see now is it's starting to turn pink. When I add it, if I don't mix it, you'll see right in the center it turns pink. And it takes a minute to dissipate a little bit, but I want to be continuously stirring in it to hold that pink for a little bit. But now I need to start adding slower. I've got it set where it's adding about a drop every second. That way we won't overshoot it. Here we go. Okay, that's what we want to see. So now we've got a really light solution, and I was just adding very slowly, just a drop, you know, like every second. And so that was just from a couple drops to where it went from clear and the pink disappearing quickly to the pink just staying now. And so I am at my end point of my titration now. And that means we need to take a final volume reading from our burette. Okay, so now we should be pretty close to level for our reading. And hopefully you can see we're between the 35 and the 36. But more specifically, we're between the second and third tick marks that are past that. So we're past the 35.2, but not quite to 35.3. And it looks like maybe we're maybe about a third of the way there. So we'll say our final burette reading for this is 35.23 milliliters. And so we have our final burette reading. Our initial burette reading was the 0.91 milliliters, and we can subtract those two to figure out how much sodium hydroxide it took to neutralize our vinegar solution or our acetic acid solution. And we'll use those values then to do our calculations of what the concentration of our acetic acid solution is. Now we have our titration data. Our titrant was the 0.1 molar NaOH, and then we have our initial and final burette readings. From those, we can actually get the volume of NaOH that we used. So we're going to take those two values and subtract them. So I would take 35.23 milliliters and subtract 0.91 milliliters. And that's going to give me my volume of NaOH that was used, which is 34.32 milliliters. And so that's the volume of NaOH that we used. And we also have our analyte information, which was our vinegar or acetic acid. And that we used 5 milliliters. And what we want to know is the molarity of that solution. So in order to get molarity from a volume, we're going to need moles. And so that's our missing piece right now, and that's why we had to do the titration. So in the titration, it is a reaction between NaOH and HC2H3O2. So a reaction between our titrant and analyte. So before we can quantify moles of something from moles of something else, we need a balanced chemical equation. So our reaction is between NaOH and HC2H3O2, and we need to predict the products of that reaction. To do that, you would do that just like for precipitation type reactions. You break the species up into their cations and anions. So we have Na plus and OH minus, and then we have H plus and C2H3O2 minus. And now you swap ion partners. The Na plus is going to go with the C2H3O2 minus, and that's going to form NaC2H3O2. And then the H plus goes with the OH minus, and that forms H2O. And so then we can put all of that together, and that gives us our balanced chemical equation, which is NaOH plus HC2H3O2 going to NaC2H3O2 plus H2O. And the reaction's already balanced, so it's ready to be used for stoichiometry. Now we can put our data with our reaction. We have 0.1 molar NaOH, and we have 34.32 milliliters of that solution. And the HC2H3O2 we have 5 milliliters of, and we want to know its molarity. So what we need to get molarity is we need moles first. So we're going to have to find that even though that's not asked for. And we're not given any other information about that acetic acid, but we have our balanced chemical equation that relates it to other substances. So all we need to know is the moles of something else. And in this case, we know about our NaOH. We know the molarity and we know the volume. So we can take those two things and get moles of NaOH. And once we have those moles, then we can get the moles of the acetic acid by using stoichiometry. So that's kind of our plan. Step 1 is to find moles of that NaOH. Step 2 is to find moles of the acetic acid, and then step 3 is going to be to find the molarity of that acetic acid. So we can calculate our moles of NaOH using the concentration we have and the volume. It's helpful to remember that that capital M breaks down into moles per liter, because then we can do this using dimensional analysis. So we want to cancel the liters and get moles out of it. So we'll use that as a conversion factor. So I'll start my calculation with the 34.32 milliliters. I'm going to convert that to liters. So I put milliliters on bottom, liters on top. 1 liter is 1,000 milliliters. And so that unit is going to cancel. And then I can multiply by putting liters on bottom and moles on top. So that's my molarity. And so that's the 0.1. And it's 0.1 moles per 1 liter is that capital M. And so the liters are going to cancel out. And that is specifically NaOH. That's moles of NaOH because that's the concentration of NaOH. So I can do that calculation and get moles of NaOH. And that gives us 0.003432 moles of NaOH. Now that we have moles of NaOH, we can convert it to moles of our acetic acid by using stoichiometry from the balanced chemical equation. So I'll start with the moles that we just found, the 0.003432 moles of NaOH. And then we don't want moles of NaOH, so I'll put that on the bottom. And then on the top, I'll put moles of what I want, which is HC2H3O2. And so again, we're following dimensional analysis where our units can cancel. And then my values for that mole to mole ratio I get from the balanced chemical equation. And you see in the balanced chemical equation, they react in a 1-to-1 mole ratio because they both have stoichiometric coefficients of 1, or we leave them off of the equation when they're 1. So I would put a 1-to-1 here, meaning that my moles are equal in this case. It's not always like that, so you can't just assume that they're equal. You've got to still do this step. So that's our moles of acetic acid. And the final step is to convert our moles of acetic acid to a molarity, or to calculate the molarity from it. You can think of it as a conversion or just a regular calculation. So to get a molarity, you need to take moles and divide by liters. And so we'll take our 0.003432 moles of the HC2H3O2, and we'll divide that by our liters. Now we have milliliters, we have our 5.00 milliliters, so you do need to remember to convert that. And we'll put milliliters on bottom, liters on top. So there's 1,000 milliliters in a liter. Okay, so this is all on the bottom. So if you do that part, that'll cancel milliliters, give you liters on the bottom. And if you calculate it, you'll have actually 0.00500 liters. And that's what you're going to be dividing by. So if you punch that in the calculator, you should get 0.6864 molar HC2H3O2. Okay, now for the final answer, we need to consider sig figs. So based on what I have written down here, the molarity that we started with was only 1 sig fig, unfortunately. The volume that we measured from the burette was 4 sig figs, and the volume we measured with that volumetric pipette was 3 sig figs. And so in our multiplication division calculations, we're going to keep the fewest sig figs, and so we should actually report our answer only to 1 sig fig. So we would say our vinegar solution or our acetic acid solution is a 0.7 molar solution of acetic acid. And so that would be our final answer for that titration.